couple abroad during final exam week. So I decided to change the final exam date. And and one more announcement is today's class is my last lecture, right? So this Wednesday is election day, Memorial Day, so 8th, right? From Wednesday, it's all yours. It's your turn, right? You come up here, I sit there. We give you a presentation. Right? 8th, 13th, your presentations, and 15th, a final exam. 20th, also your presentation. Okay, any question before class? So we are going to finish up TrustZone discussion today. We are going to play the game, right? Ghost Radar game, right? Probably Gyeongnam, you go first, right? Because you are traveling. Gyeongnam is number 1, and probably then we are going to play, Ghost Radar, right? This Ghost Radar, right? That game to select lucky, winners. Yes. I think that is my favorite, actually, in the class. Okay, so to refresh your memory, TrustZone is providing, 2, words. Secure word, and normal word. And to make switches between these two, you have to go through, monitor mode. So here, monitor mode. So from secure word to normal word, you have to go through. That is a recommended way of doing word switching. And from normal word to secure word, you have to do the same thing. That is the recommended way. And how do you differentiate these two? Right? You can check out. You can simply check out, system register, SCR, right? Secure configuration register. There is a NS bit in SCR register, system register. If NS non-secure name, right? Non-secure. NS bit is what? NS is equal to 1. Then you are in normal world. And NS bit is 0. Then you are in secure world. It is specific. Right? So in secure world, you can probably secure world. You have all the power to touch everything, right? So you can change SCR register. Probably you can use MCR instruction or processor instruction to change that SCR register. Then you don't go through actually monitor mode. You directly switch to normal mode. But that is not. 뭐가 있나? 카메라? Probably you check out this. Okay, this example. So again, to switch from secure to normal world, you can simply use MCR instruction to change the NS bit. But that is not recommended way. It is very brutal way to change to do word switching. But you can do this. You can do word switching by changing that NS bit using MCR instruction. But in secure world you can do that, but in normal world you cannot. That is obvious, right? You cannot use MCR instruction to change NS bit to 0. then you go to secure world, right? Then that is not permitted, right? So that is obvious, right? You don't have enough power, no more world, right? So you cannot do this. If you do this, I think some exception will be generated. Exception. So today we are going to talk about two different ways to do word switching. First one is using SMC instruction, secure monitor code. It's monitor code. That is instruction like SBC instruction. If you remember software interrupt instruction, SBC, that is used to do system code. So it is much like system code. You are executing here SMC instruction. Then you can go to this monitor mode. So same thing here. In normal world, you execute SMC instruction. Then you can go to monitor. Second way to do word switching, interrupt or exception. So we will talk about this too. So except interrupt is generated here, then you can that will take you to monitor. Interrupt is generated here, you can take it, that will take you to this monitor. Depending on register setting, we will talk about it. And one thing I have to refresh your memory is, in my opinion, ARM architect was trying to make minimal changes to CPU. So almost everything inside CPU is shared between secure world and normal world. Right? For example, register type, general purpose register, ALU, right? Neon engine, floating point, almost everything is shared, but some system registers like VBAR, right? Vector base register. That is pointing the start location of interrupt vector table. In secure world, also you have separate interrupt vector table, and you have a bank register VBAR. Bank means separate copy, physically separate register. So if you are in secure world, then you are accessing this VBAR. Okay? And switch it to normal world, you are accessing this VBAR, physically separate register. And some more system registers like the translation table based register. We haven't talked about virtual memory, so we'll skip this. And you need separate interrupt vector table because you want to run full-blown stack, full-blown software stack like that. Right? So if you think about computer system, right? Interrupt and exceptions are generated continuously. Think about your x86 computer system. You are in Linux system. You are in normal world and Linux or Windows running here, and applications running on top. Then many interrupt and exceptions are generated. Somehow you have to handle that event. Same thing goes to secure world, right? Secure world, you want to run full-blown software stack. So that means the interrupt exceptions are generated. That's why you need a separate vector table. So interrupt the exception, right? And system code and some abort, right? But if undefined instruction. So in secure world, but if you encounter some undefined instruction, somehow you have to handle that situation. Right? So you need separate vector table. So this one is about CPU. Then TrustZone is not only applied to CPU but also to memory and I/O devices. Memory and I/O. I gave you one example, right? So one. So in the hardware design phase, the computer system design phase, you can say, okay, first 1 gigabyte. That should be accessed when you are in only secure world. this green part. The second 1 gigabyte should be accessed in normal world, right? You can impose that kind of restriction by physical connection. So ARM is providing that AMBA signal, AX protection, AX protection. Depending on the world you are in, CPU, you are in secure world, then protection bit, this bit will be 0. Same thing, right? NS bit, NS. NS1, normal world, NS0, then secure world, right? Protection bit is 0, then CPU is in secure world. Protection bit is 1, then CPU is in normal world. So using that signal, you can create your own, the customized hardware system. And also, IO devices. Right? Some IO devices should be accessed in only secure world. Right? So using that signal, you can make the connections. And in the Zynq case, Zynq is providing some programmable way of doing that configuration. Let me show you that. So if you scroll down, so Zynq is one implementation of Cortex A9. Xilinx licensed that IP, then customized it, right? So during that process, they are providing some TrustZone related registers, like this. These are called system level control registers. Okay? System level control registers. So, for example, this register is providing this register. Using this register, you can set the can you please see? Okay, using that register, you can set world access restriction. For example, main memory. Right? Main memory is logically divided into that 64 megabyte chunk, 64 megabyte block, and first 1 megabyte should be accessed in, for example, secure world. If you set that bit to 0, then the first 64 megabyte should be accessed in secure world. Set this one to 1. That bit TG, DDR, RAM, and 32-bit register. I think each bit, this bit is talking about this 64 megabyte, and next bit talking about next 64 megabyte. So 0, that means first 64 megabyte should be accessed in secure world, right? And 1 normal world, and so on. So Zynq is providing some programmable way of doing that configuration, world access restriction. And to access the register, because it is very sensitive information, security information. So you have to unlock. It is providing some protection. This one, Mingyu, can you please read this one? Okay, so the TrustZone related registers are very sensitive, contains very sensitive information. Right? And to change that information, you have to unlock. Right? Zinc is providing that capability. So you have to lock register, right? If you write this value 767B to that register, then it is locked. You cannot change it. And then to unlock, you have to do this. You have to write DF0D to unlock register. Then you can change those your system level control registers like this. Easy. That is for protection. So anyway, the point is, Zinc is providing some registers you can program to set world access configuration. Okay. And let's talk about now the world switching. Okay. Transition between these two words. So Donna, please. Okay, thanks. The first way to do world switching, SMC instruction, secure multiple instruction. That is SMC, secure multiple instruction. And you can execute SMC instruction only when you are in privilege level 1. Privilege level 1. PL usual mode is PL0. So you cannot, that means you cannot execute SMC instruction in usual mode. So system mode and IRQ mode, supervisor mode, you can execute SMC. TrustZone, you have three kinds of vector tables. 3 vector tables. First vector table is secure world, second normal world, and third one is monitor. So the location. Third location of vector table we bar in monitor mode. You have MV register. Using MV bar register, you have to set the start location of vector table. So that is the information about vector table. Secure world, right? You turn on computer system, Zinc device, then you go to reset. If CPU execute the reset vector, the branch some reset, that. Then offset 04 undefined instruction, SVC, supervisor code, software interrupt instruction, and abort. That's not used. Okay, hypervisor. If supported, used, but not supported, not used. IRQ. Same thing goes to here, but there's no reset vector. No reset here. No secure and monitor. Because you turn on the CPU, and you are supposed to go to this secure state. That makes sense because otherwise you cannot set, you can configure the system. You cannot do initialization of the system. Right? You should go to the most powerful state. That is this one. And monitor mode, there no vector, and if you execute SMC instruction, I'm there to show you. So this one is one example. Take a look at this. So in the example code, right, secure world code, normal world code, and monitor mode code, assembly. So there is a interrupt vector table, and you have to set VBAR. Okay, and here same thing goes to here and here. So if you execute SMC instruction, that will take you to that point. So CPU will execute this branch SMC handler instruction. Okay. Same thing goes to here in normal world, right? If you have enough privilege to execute SMC, that will take you to this handler on time. Okay. And during this transition one and one, hardware will do that kind of operation. Hardware. Remember interrupt discussion we did last time? Let me show you this one. So interrupt, right? Interrupt is generated and hardware will do this operation. The point is, what is the message? So you execute some program, right? And then you got interrupted. Then you make a transition to vector table. Right? During this time, CPU is trying to save some information, right? Save some information about your program status. Right? First one, CPSR, right? CPSR will be backed up to SPSR because you are going to change CPSR register, mode bit, right? Interrupt masking bit. You are going to change that, right? And then link register will be modified to updated to the location of next instruction. Then what else? CPSR mode bit will be changed to IRQ or FIQ, depending on interrupt type. Right? Then I bit, F bit will be set to 1 to mask interrupt. Right? And finally, program counter will be changed to 01C or 018 for normal interrupt, 01C for fast interrupt. That is happening in case of interrupt, right? Similar operation, actually almost the same operation, okay, is done. Okay, done during that transition. Look at this. CPSR is backed up. So you are executing some program in normal world, right? Then you want to preserve the state of your program, right? So CPSR is backed up to SPSR in monitor mode. And address of next instruction, okay, in this example, a location of addition instruction will be saved in link register. Then mode bit will be changed to this one, 1, 0, 2 zeros and 1, 2 ones and 0. That is monitor mode. Then AIF will be set to 1. That means you are masking interrupt and exception. Then program counter will be changed to 08. And you want to execute that exception. Okay. Similar operation. It's almost the same operation is happening, right? When you execute SMC instruction. So what is the purpose of executing SMC instruction? If you execute SMC here and SMC here, then you want to do word switching. Right? Context switching, word context switching. So that is done by hardware, and the rest should be done by software. Like task switching, right? interrupt generation, then hardware is doing minimum amount of operation. If that operation is not done by hardware, then you have some problem. That is because hardware is doing that operation. Same thing goes to here. Right? Okay. Hardware is doing that operation. If hardware is not doing that operation, you have some problem. Right? So then the rest, right? The rest should be handled by software to do context switching and word switching. Right? So let me show you one example. So this one is an example code in SMC handler. We assume from normal world we execute SMC instruction. Okay. Then you go to the monitor mode. SMC handler. Right here. Then you jump to SMC handler. That is the one. SMC handler. So what we want to do is essentially this one. So G1, please. Okay, so if you think about what you have to do in SMC handler, I like you to think about what you have to do in the SMC handler. So the thing is, you want to do word switching, right? Some task is running here. So you want to push the context of your task in normal world. Then what? You want to restore the context. Think about your task switching. It's like task 1 is running here, right? And you execute SMC instructions. And you here, then task 2. So task 2 should be resumed. Task 2 should be resumed, right? Task 1 should be stopped. And task 2 in secure world should be resumed. Then what do you have to do? So what you have to do is in SMC handler, right? In monitor mode, you have to first figure out who called monitor mode. Normal world called monitor mode or secure world called monitor mode. If normal world called monitor mode, then you have to push T1's context, right? Push T1's context and pop T2's context, then resume. If monitor mode was called from secure world, opposite should happen. T1 push T1's context, T2 for T2's context, and pop T1's context, right? And resume. Right? So the first thing you have to do in monitor mode is which word take you to this monitor mode, right? That's why first instruction is doing what? Reading SCR register, system configuration register, to check out this NS bit. So by checking out this NS bit, you know the which word the code this monitor mode, right? So you read SCR register, then you execute this TST. What is TST? Test instruction. Then R0 with 1. Then essentially you want to check out this NSB. This is least significant in SCR register. So that instruction is doing AND operation. And R0 then 1. Sorry. Then assume that SMC instruction is called from a normal word. Then NS is 1, right? Then 1, right? 1. Then output is output is 1. Then NGCB. Next instruction is checking this 0 flag. Because output is 1, 0 flag is not set. 0 flag is still 0. End operation output is not 0, right? So 0 flag is 0. 0 means not 0, right? 0 then set 1. Right? So then next instruction. Then next instruction is the XOR operation to toggle this R0 register. You read SCR register and put it into R0 register. Then you want to toggle because you want to do word switching. So you want to change NSB to 0. So XOR instruction. Then MCR instruction is updating SCR register. Only NS bit will be toggled. Then update SCR. So that is word switching. Then the rest 3, 4, that code is doing push and pop operation. And we are assuming, I need to explain this. We are assuming that memory status. So it all depends on how you architect, how you design software architecture. So, but in that moment, we are assuming memory, and same memory. Then that location, this location contains stack pointer. For secure word. Stack pointer. That location contains stack pointer. So here you have this one is stack for secure word. So address is decrementing like that. We are using full descending. Let's say location low, high. So stack pointer is pointing somewhere, full descending, right? Something like this. And we have, separate location that is storing stack pointer for normal words. Okay? So this one, for example, stack for normal word. Let's assume that is pointing that location. Okay. So what you have to do is you have to read stack pointer. This is stack pointer and this is stack pointer, and make a decision. Push and pop operation depending on where you came from. If you came from normal word, then you have to do push operation, right? You have to do using this stack pointer. You have to do push operation. Push CPU context. Okay. Then pop operation. Pop this file. Pop this file to CPU. If you came from normal word. If you came from secure word, to monitor mode, then opposite, right? Using this stack pointer, you have to do push operation. You have to do push operation, push the stack pointer before this, then pop operation. Right? So depending on where you came from, right? So next code. So this code, get this. So here using TST instruction, we set flags. We set NGCB flags, G flags. Here we are assuming you came from you went to the monitor mode. Because normal word you call SMC instruction. Right? That means zero flag is 0. Then look at this. Load EQ. Load instruction. Suffix is EQ. The next one is not equal. Equal, then that instruction will be executed. Not equal, then second instruction will be executed. So in this case, not equal, right? Not equal. So the first instruction, LDR EQ will be silently ignored inside the CPU. First instruction is not going to be executed. And second instruction will be executed. So second instruction is doing what? It is reading. It is reading from that, reading from this location. Second, LDR, right? Load LE. And E R0, and S, that instruction. Reading from that location and storing to, R0. So location, not yet. So their location. The location is this location. Okay. Then next instruction, LDR R2 R0. From this location, you are reading this guy to R2. So R2 has a stack pointer now. R2. And then R2, stack pointer for non-secure word. Right? SP for non-secure, normal word. Then next instructions. Here, same EQ and NE. EQ and NE, right? EQ and NE. Zero flag is still 0. Okay? So first instruction will be ignored, right? And second instruction will be executed, not equal. So second instruction is doing what? LDR NE R1 from this is secure. The location of this label. Okay. Then LDR R3 R1. So we are reading from the location storing to R3. So stack pointer to the secure word. R2 stack pointer to normal word R3. Stack pointer for secure word, right? Then now next instruction. Next, for instruction is doing push operation from this location. Using this one as a base, using this one as a stack pointer, you are pushing CPU context. R4 to R12, right? R4 to R12. Then SPSR is saved to R2, R4, and R4. Then link register will be pushed as well. R4 to R12, then SPSR. So here, remember full descending, low, high group, R4 to R12. Then R4, so SPSR, right? SPSR, then link register, push it. So that is the status. Then this instruction is doing opposite, right? From the stack, you are restoring the context, right? Opposite operation. So in this example, we are assuming that normal word want to pass argument to secure word, right? Sometimes you want to pass some argument, right? To this to the full lead, right? This is full long and this is full lead. Right? You have to pass some argument. Those arguments are passed through this R0 to R3 register. So here we are doing push operation. Push operation goes what? Inside this SMC handler, we need to use R0 to R3. If you look at the code, R0 is updated here, R2 is updated, R0 to R4, R0, 1, 2, 3, 4. R1, R3. those registers are updated. That is why before you use those registers, you do push operation, and later on you do pop operation. And then the last one is exception return, right? Exception return. Move S. Then PC is updated, and CPSR also updated. That is one example of word switching no code. Any question about this? So I got this code from that reference. I think if you go to our class page, scroll down, and I got this code from this one. TrustZone example code from EB. Right, this one. You can take a look at this code. Okay, so this is the first way of doing word switching using SMC insertion. Now let's talk about second method of doing word switching, interrupt. Kun, can you please? Okay, then next one, someone, can you please? Okay, so before we talk about this, I need to show one system register. So this SCR register, the LSB is NS bit, right? Non-secure bit. So by looking at this, you know which word you are in, NS bit, and some important field you have to look is FIQ, then IRQ handler, and external abort handler. So bit, this one, 1, 2, 3 is 3 bits. 1, 2, 3. So IRQ bit is set to 1. Okay, 1. Then interrupt will take you to that bit. I bit is set to 1. Then normal. Suppose that normal interrupt is generated here. Then that will take you to monitor. If you set this bit to 1, IRQ handler is. Same thing goes here. If IRQ bit is set to 1, then interrupt is generated. Then that will take you to monitor. Otherwise, it is not taking you to monitor mode. You are jumping to some vector like this, this. set to 0. IRQ is set to IRQ not taken to monitor mode, right? Set to 0, and interrupts generated in normal world, and you jump to some entry in this vector table. If IRQ is set to 1, then that will take you to the monitor mode. Same thing goes to FIQ, fast interrupt. If FIQ is set to 1, then fast interrupt is generated in normal world, then that will take you to the monitor mode. And external abort too. External abort. External abort, we haven't talked about external abort, but that is about one example. One good example is parity error. While you are accessing memory, you got some problem, some parity error. Okay, data got corrupted. Right? So then exception is generated. You access cache. Cache is also providing parity error. So data is corrupted. Right? Then abort is generated. In that case, also you can go to monitor mode and the bit setting. But I don't know why do you want to use that bit. It is, I think, not typical case of using this external abort to the world switch. I don't know the application example. IRQ, FIQ, that is making sense, right? Timer interrupts generated, then probably you go to different world. Right? But external abort, I don't know why. Why do you want to do that? External abort, right? Parity error. Right? Then why do you want to do world switching? But anyway, it is configurable, right? If you set it to 0, then you stay in that world, right? You don't do world switching. And ARM's, recommendation is we in the GIC we talk about group 0 and group 1 interrupt, right? Some I/O device interrupt can be there are two groups, right? Group 0 and group 1 supported in GIC. So you can allocate. Okay, timer interrupt, you are in group 0, and UART interrupt, you are group 1. You can set configuration like that using some register in GIC. And typical example, this one is probably better. Group 0 interrupt, group 1 interrupt always delivered through IRQ. Group 1 interrupt, group 0 interrupt can be signaled, can be delivered through FIQ. If you set this bit FIQ enable to 1. Okay, so this one is almost everything I need to talk. So this is the one. It's IRQ, right? IRQ. Let's say IRQ is set to 0, then what? Interrupt is generated. Then you stay in that world, right? In normal world. In vector 2, you access that interrupt. But if FIQ is set to 1, the fast interrupt is generated. That will take you to monitor mode. Same thing will be here. SCR FIQ is 0. Fast interrupt is generated. Then you stay in secure world. So one example. So SCR IRQ 0, IRQ 1. Then no interrupt is generated in normal world. You stay in the normal world. But in secure world, interrupt is generated, you go to the monitor, to the world switch. Let me show you now example 4. You can download this one, TrustZone.7G. So I already created project, and this is the one. This project is composed of 3 assembly files, secure mode code, interrupt vector table, right? And normal world code, right? Here, separate vector table and monitor mode. Right? Separate vector table. Okay. Then let me explain so important. So here, you turn on and download, turn on the board and download it to the board. Then you stop here, right? In secure mode. Then you want to change system level control register to change trust zone related registers. Jinx is providing, right? So I told you DDR, right? DDR RAM. Okay. If you set to all ones, then memory DDR can be accessed by secure world and normal world. Right? All one. NS speed is 1. Then secure world can access and normal world can access that memory. Right? So before change this kind of system level control register, you have to unlock, right? Because it is protected. Right? So this is a procedure: unlock system level control register. So based on that specification, right? Write this value to unlock register, and you are free to change that trust zone related registers. Right? So then after changing that, you are locking this one. Right? Then you cannot change those registers. Then user code, right? Stack pointer setup and vbar setup. Right? Secure vector table, right? Using MCR vbar setup, right? And monitor mode vector table. Go to this one. So monitor mode vector table is updated, and MMU, don't worry about this. Then this one, SCU, non-secure access control register. That register is talking about, it is all about register. Right? Non-secure access control register, you can set world access configuration. Right? For example, CPU 1 private timer. Private timer should be accessed in secure world or normal world. Right? Those stuff. So if you set everything to 1, then you can access these I/O devices in normal world. Normal world means your secure world can access those I/O devices. Right? So I set that register to FFF, okay. 12-bit. FFF, that means these I/O devices can be accessed in normal mode. Then secure control register. Why I'm doing this? SSL. This one is important register, right? You have to look at. Read the register, then doing OR operation. Oh, okay. Because of this, IRQ. Okay, interrupt is generated. Then you want to go to monitor mode. Right? Show you. So this IRQ bit, right? The second bit, IRQ. So I want to set this bit field to 1. Bit field to 1. That means IRQ will be taken to monitor mode. So that is why I'm doing OR operation. Read SCR register here. then doing OR operation, then update, right? Then using MCR instruction. And then user interrupt control setting, distributor, and CPU interface setup. So here we want to use private timer. So the scenario is, to show you. The example code, you go to secure world, right? Then here you are doing some initialization. Then then using SMC instruction, you go to monitor. It is like a booting process. Then from SMC you do something, then you go to the normal world. And in normal world, you are supposed to execute your usual application, right? So application, while executing application, interrupt is generated, IRP. Timer interrupt will be generated. And in secure world, we set So in secure world, we set during initialization SCR IRQ to 1. So that means if interrupt is generated, then IRQ is 1, then that will take you to monitor. I want to see interrupt is really taking you to this monitor. You want to see that. That is the example code, right? So booting process. From secure world, you are booting. Right? System is booting. So some system initialization, GIC setup, and SMC instruction you take to monitor, either take it to monitor, to something, then normal world. Right? Here you are starting private timer. And you can set private timer because we in the initialization code. SCU, which is register, so many register. Some register is set, right? That is allowing you to use private timer in normal world. So IO device, the TrustZone is applied to IO device, right? So private timer, can be accessed in normal world by setting up what? By setting up this register, SAC, non-secure access control register. So we set to or F. That means you can access private timer in normal world. So that is what we want to do. Right? So still we are in secure world code. Distributor setup, interface setup, then interrupt enable, CPSR, right? CPSR interrupt enable, then execute SMC. SMC then either take you to monitor mode, right? That vector. SFC handler, then this code, right? SMC handler. Right? In the handler, we are touching LED. Right? Touching LED, then we want to go to normal world, right? To go to normal world, this function, this normal world, right? This code. Then you are storing the location to link register, and SPSR is updated to 1F. 1F is system mode, right? So using LR SPSR, you want to go to normal world, right? So finally, you want to execute. You are executing this one. Then LR is updated to program counter, and SPSR will be updated to CPSR. Switch it to normal world, right? This one reading So before, right? Before it's still monitor mode, right? So here you are toggling what NS bit, SCR NS bit. So let me execute this code, right? So better to show you. Very complicated, so a little bit hard to explain. Okay, stop to here. Then don't need memory. 5. So check out this register. If you read, then 1 means I think locked. R1 1 locked status. If you get 1, then locked. It is not. You cannot update your system level control registers. So then, according to that protocol, we are writing that magic key df0d to unlock register. Okay. So now check out same code, right? Same code. R1 same code, right? Then it will be changed. Now 5. So 0. That means it is unlocked. So now you are free to change that system register. And 5 DDR. Skip this. So now lock. Using that magic key, we are locking the system level control register. No more update. Okay. So R1 will be 1. So user stack point setup. VBAR setup, vector table in secure mode, and monitor mode vector table setup. Okay. MMU, don't worry about this. Then IO, private timer access in normal world, right? We want to do that. That is why. And using SCR IRQ bit. Okay, I want to set this bit to second bit to 1. So that means interrupt is generated. That will take you to monitor mode. Right? User GIC setup. Skip this. Okay, now interrupt enable that SMC now, right? Secure monitor code. So if I press F5, this one will take you to this code, monitor mode code, right? Secure mode code, monitor mode code, normal mode code, right? So if I press F5, then monitor mode, right? It will take you to vector 08. So SMC handler. So reading something, doing some turn on LED. Okay, turn on these 2 LEDs. Then we want to go to normal world, right? Normal world task. That is why store this label to link register and LR2. So it is like exception return, right? Exception return, right? Because we are executing this instruction. So returning from interrupt handler. Right? So in ISR, right? Main and interrupt is generated. Then you jump to ISR. Then at the end, you are executing move S instruction. ECLR. Actually, SUES. Then you go back to interrupted place. Right? So this instruction is used for interrupt exception return or interrupt return from interrupt, or return from exception. Right? We are using same procedure. Right? But before executing this code or move as instruction, ECLR, you have to set LR2 the label and SP SR2 to whatever you want to set, because that instruction will update. It's doing two things. First one, PC updated. Second, CPSR updated, SPSR. So here you are setting. Here, link register. In the booting sequence, you are setting link register and SPSR with whatever you want, right? Then you execute move as instruction. So it is like exception return. Right? SCR register. Before we execute this, C1, I think. Scroll it down. There is that. We have SCR, right? Secure configuration register. Right? Now 2. 2 means what? 1 0 in binary. That is what? 1 0 in binary, right? That means 1 1 0. Then IRQ bit is 1. That means interrupt will take you to monitor mode. 0 means you are in secure mode, right? Secure. Last bit is 0. Non-secure bit. Non-secure bit is 0. Then you are in secure mode. Okay. Then read MRC. Read SCR stored into R4 register. And R4, then you are doing OR operation to set NS bit to 1. Right? That means normal word. Right? Okay. So here, if I press F5, this bit, I think SCR will be changed to 3. 2 to 3, I think. 3, right? 3. Then exception return. Then it will take you to that normal world code, right? This one. Press F5. Normal world, right? Normal world code. Right? So here I'm setting up a vector table, my normal world vector table, right? VBAR register. Then what? So private timer, right? We went through this code, right? Private timer is configured with that code, and we can do that because we touch it that register in the secure, secure code. We are allowed to access private timer registers in normal world because we changed this this register. So 5 timer setup, then same code, right? Private counter, right? You want to check out. Countdown is actually happening. So here forever loop, right? Forever loop. So I don't want to type this 1 million times. Timer counter is set to what? Timer interval, 1 million, right? Roughly 1 million, right? So I don't want to type 1 million times. So let me press F8. But before that, let me set breakpoint. Oh, I already set up breakpoint here, then probably here. Okay. So monitor mode, vector table. So if I press F8, it will stop somewhere, right? Oops, what is this? Okay, let me see if I can. Okay, let me do it again. Secure world, monitor mode, let me stop here, probably. Normal world, right? Stop here, press F8. Okay, I set up breakpoint here, the monitor mode, that is why. Stop. F8, one more time, then stop. Normal world, okay, F8. Okay, stops here. Because interrupt is generated, it will take you to this monitor mode. Vector 18. Monitor mode, vector type 18. Then F5. Then something, according to that, protocol, you have to program, read from, acknowledge register, then private timer status, bit clear, end of interrupt stuff. Okay. Press. Then return from interrupt. Okay, monitor mode still, right? If I press F5, then you will go back to, I think, monitor, normal mode. Right? Right, this forever loop, right? Forever loop. You are still, right? Okay. So if I press F8, because timer interrupt is set, timer is set as, auto reload mode. It is periodically generating interrupt. So let me press F8. Interrupt is generated, right? So check out this LEDs, right? LED. If I press F8, stop here. Every time I press F8, LEDs are toggled, right? It stops, it's monitored, this vector. One simple example. Okay. Any question about this? Probably you can. You want to do some testing by doing this, right? In user mode, right? You are generating SMC. So probably you want to do that. Okay, so F8 stops handler in monitor mode because we executed that SMC instruction. CPU executed SMC instruction in secure mode. And press F8, then it will stop in normal mode code. Let me press F5. Okay. Normal word here, right? NOP, then next instruction. SMC instruction in normal word. It will take you to monitor mode. This is monitor. So you can play with the SMC instruction, then IRQ, the interrupt, right? Okay, any question before closing up? That is everything I have this semester. Okay. So we are going to play a game, a ghost-like game, a radar game, right? So we are going to determine the lucky, few students next Wednesday during that presentation day. And Gyeongnam is number one, first one, because Gyeongnam is taking commerce. Probably, I think 4 to 5 students can present in one day. We have 1 hour and 50 minutes. So each of you can take 15 minutes. 10 minutes presentation, 5 minutes Q&A. That means 5 students can present in one hour, one class. Okay, any other questions? Okay, see you. That's it.
그걸
아,
좀 보면 콘퍼런스가 20일에는 제가 수업으로 들어서 저도 첫날에
언제 간다고?
17일 그 기말고사 다음에 기말고사 다 다음 날
10 우리가 15일 날 오기로 했잖아.
네 17일에
17일 날. 그러면 먼저 해야겠네.
네네
먼저 하는 8일 날 먼저 하는 게
네.
오케이.